Welcome back. A rapidly emerging PV technology is that of the perovskite solar cells. Perovskites have seen a tremendous increase in initial efficiency in the recent years. The first perovskite cells with a conversion efficiency of around 2.2% were only reported in 2006. Non-certified cells efficiencies higher than 23% have been reported only 17 years later. So the objective of this video lecture is to get familiar with the material and lattice properties of photovoltaic materials based on halide perovskites and their processing methods. Secondly, we will discuss the most important device structures and the operation mechanisms of the perovskite photovoltaic devices. Thirdly, we will discuss the challenges this emerging PV technology is still facing, including some of the approaches to tackle these challenges. So, what are perovskites? Perovskites are minerals with the general formula ABX3, where X is an anion and both A and B are cations. An anion is a negatively charged ion, where a cation is a positively charged ion. The mineral perovskite with the formula calcium titanium oxide is named after the Russian mineralogist Lev A. Perovsky, who lived from 1792 to 1856. The figure illustrates the general cubic crystal structure of perovskites, ABX3. For photovoltaics, organic, inorganic perovskites are used, where the large cation A is organic. Often methyl ammonium, abbreviated with Ma, or formamidinium, abbreviated with Fa, is used. X is an halogen, such as iodine, chlorine, or bromine. Often these mixtures of halide materials are used. The cation B usually contains lead, while tin can also be used. The halide perovskite materials have received extensive attention in the PV research due to its promising physical properties. Let's discuss some of these properties. Based on absorption measurements and simulation results, it can be concluded that the halide perovskite solar cells have a direct band gap. Here we see a typical absorption spectrum of methyl ammonium lead iodide perovskite material. It has a relatively sharp band gap. Let's include the absorption characteristics of gallium arsenide. Gallium arsenide is, as you know, a direct band gap material and therefore has a sharp band gap. We can see that the band gap of perovskite is not that sharp, but the methyl ammonium lead iodide material is getting pretty close. If we add the absorption coefficient of crystalline silicon to the graph, we can see a clear difference. Crystalline silicon is an indirect bandgap material for wavelengths above the 400 nanometers and has a significant lower absorption coefficient. In contrast, the direct bandgap properties of the methyl ammonium lead iodide results in a high absorption coefficient in the visible part. These absorption characteristics make the material suitable to be used as thin film photovoltaic material. Secondly, methyl ammonium lead iodide has a much sharper band gap when compared to, for instance, crystalline silicon. The electrical properties are highly interesting as well. The perovskite material does not have a field-dependent exciton dissociation. Also, due to its defect tolerance, the low trap densities in the bulk results in a long intrinsic diffusion length and relatively long carrier recombination lifetimes. The band gap can be tuned by the alloy and can range from 1.3 electron volts up to 2.3 electron volts. The standard methyl ammonium lead iodide perovskite has a band gap of 1.55 electron volt or 800 nanometers expressed in wavelengths. The halogen anion X of iodine can, for instance, be replaced by bromine. The band gap of methyl ammonium lead bromide shifts to higher energy up in the visible range. It has a band gap of 2.3 electronvolt. That's a wavelength of 539 nanometers. In reference to standard methyl ammonium lead iodide perovskite, the cation based on the 4 valence element, in this case lead, can be replaced by the 4 valence element like tin. The band gap of methyl ammonium tin iodide shifts to the infrared. It has a band gap of 1.3 electron volt or 954 nanometers expressed in wavelengths. The organic cation methyl ammonium can also be replaced by formamidinium. This has a minor effect on the band gap in reference to the methyl ammonium lead iodide. The band gap of the formamidinium methyl ammonium lead iodide has a small redshift. Its value is in the order of 1.5 electron volt, which corresponds to a wavelength of around 827 nanometers. Of course, band gaps can be tuned using the mixtures of these different halide perovskites. For instance, for hybrid tandem applications, higher band gaps than that of methyl ammonium lead iodide are required. Such applications require halide perovskite materials based on a mixture of methyl ammonium lead iodide and methyl ammonium lead bromide. Perovskites can be deposited using several processing methods. Various deposition techniques can result in high-quality perovskite films. The method most explored on lab scale is solution-based crystallization using a spin coating of a precursor solution. Processing has been further developed and post-treatments have been successfully applied in which anti-solvent ethyl ammonium lead iodide or an intermediate compound are used. Spin coating works fine on lab scale sizes, however it's not straightforward to upscale this process technique on large module areas. So many other methods have been reported like blade coating, slot die coating, spray coating, inkjet printing, co-evaporation, flash evaporation and pulsed laser deposition. Note that some processing methods are easier to scale up to industrial levels than other methods. The perovskite layer is a polycrystalline layer. This means that the layer consists of grains with different lattice orientations and grain boundaries. As grain boundaries are surface entities in the bulk that facilitate defects, they can enhance the recombination of light-excited charge carriers. By increasing the grain size or decreasing the amount of grain boundary surfaces, the diffusion length for charge carriers could be increased from 1 micrometer up to more than 100 micrometers. However, some studies suggest that in some halide perovskite materials the grain boundaries can act as conduction paths, which benefit the transport of the charge carriers in the absorber layer as well. The exact role of effects of grain boundaries on the performance of halide perovskite solar cell is still a subject of research. In the next video we will discuss the different device structures of halide perovskite solar cells. So see you back in the next video.